Thank you. So, as you can see, oh, as you can't see. Okay. This is going to be a technical talk. Actually, I should make that clear. There's relatively little APL in this. But just for listeners of a nervous disposition, it's rather prettier APL than we covered in the workshop yesterday, which was singularly horrible for reasons we won't go into. So my interest in computing and robotics and neural networks really goes back to when I was quite a young kid in 1956, when Robbie the Robot graced our screens, and the newspapers were constantly full of stories about electronic brains, which is the way that we all referred to computers in those days. And I thought this all sounded fun. Didn't do much about it. Well, if you want to find out how I got caught up in computing, I'm going to be talking a bit about that on Thursday. But that interest tied in with an accident of history. I was very lucky when I went to university to be supervised by a guy called David Marr. David at that stage was a recent math graduate. I was majoring in maths. But he had decided that brains were much more interesting than pure mathematics. And he was spending 2 or 3 days a week coming down to London, working with a team of neuroanatomists who knew pretty much as anybody knew about the way that a particular bit of the brain worked. And about 2 years later, he published a paper which he had, based on the research he was doing then, on the way that the cerebellum works, the cerebellar cortex works. And a couple of years after that, he came to London to give a talk which I attended, and I got absolutely fascinated by the way that, what he thought this did and the way that it worked. The cerebellum is a bit of the brain that most people haven't even heard of, and yet there's an old joke by neuroanatomists, you can tell from this that they're not really very good at jokes, that of the 10 to the 10 neurons in the human brain, 10 to the 11 are in the cerebellum. Okay. There's an awful lot of hardware compressed in that space. And the surprising thing about it is that its physical structure, its anatomical structure, and the connections between the nerves are simple and very regular. It's not quite so true for the rest of the brain. So this group, under Professor Bindley, were trying to work out exactly the types of connection that existed and how things might interact. And David came up with a theory which is still pretty widely accepted with minor modifications today. And his view of what the cerebellum was doing was that it had a set of inputs which represent the context in which you perform actions, and a set of training inputs which tell you what you should do in that context. And then when that context next occurs, you'll be able to perform the action without the training inputs. So if you imagine you're learning to play a musical instrument, a guitar maybe, you'll start off playing pretty slowly and thinking fairly hard about everything you do, and you'll repeat it, and eventually those actions will become pretty much automatic, and you'll be capable of carrying them out much more smoothly. And indeed, one of the good bits of evidence about what the cerebellum does is that if it gets damaged, people can still do stuff, but they tend to move very jerkily and show poor signs of coordination. But actually, that very general description of a content memory, a content addressable repertoire of things, sounds like it might be quite generally useful. And so a few years after that came out, I started doing a master's degree at Birkbeck and decided that I was going to try and simulate David's model. I think one other person had done that at that stage, as far as the literature goes. My supervisor thought that A, I wasn't going to get the project finished, and B, if I did, it wasn't going to work. And really surprisingly, he was wrong on both counts. I did manage to burn up most of the department's computing budget on the computer that was providing computing power to the whole of the University of London. But that was just because I had to compile the code a lot to get it to work. It didn't actually run that slowly. That model really got me interested, and I tried playing around with the ideas a bit. But of course, in 1974, the way that you did exploratory programming was you got the deck of cards out again and edited a few cards and put them through the reader, and a day or so later some results came back. And that wasn't really conducive to exploratory programming. So let's fast forward to 2012, when I got very interested in the Raspberry Pi. I actually briefly ran a startup but produced extra hardware for that. But I also started exploring the idea of redoing some of that original project in a more modern language. And as Morten has hinted, the one that I picked at that stage was Python. And I made a bit of progress, but it wasn't as fast as I liked. And then 2 or 3 things happened. One was that APL became available, Dyalog APL became available on the Raspberry Pi. And I was in much more contact with Dyalog these days. And so I started reworking in APL. As far as artificial neural networks are concerned, the underlying model that you're trying to implement is a very simple model. And as it happens, that model works fairly well for David Marr's theory as well. Essentially, what most artificial neuron models do is take a vector of inputs and multiply those by weights and add a bias and apply some function. And the function is typically, it might be as simple as a threshold. Is this value greater than 0? Or it might be a bit more complex. It might be some sigmoid-shaped transfer function. But doesn't that say APL to you? Okay. If you've got a lot of those things, you're going to end up with a matrix of weights which you multiply by a vector of inputs, and then you add the vector of biases, and you apply a function, the same function to every value in the vector. And of course, that's the stuff that APL absolutely eats. So yesterday, we took a look at some of the ways that you can implement standard algorithms. I didn't talk about my my own work. I might maybe make enough progress to be able to do that next year, if I get asked. And of course now, neural networks have become a very, very hot topic again. So first question, how many people in the audience have used a neural network, directly or indirectly? Okay, so there are people here who've never used Google Street View because the thing that blurs out the faces in the number plates works out what to blur out by using neural networks. And I had an experience which I found shocking, and I was already, I'm pretty persuaded that this technology stuff is going to work one day. I took the original TypeScript for my MSc project, and took a photograph of each page with my camera and put the photographs up on Google Docs and got back text. For the Algol code, which was in the original project, that was not terribly clean, because I'm guessing that Google Docs hasn't seen an awful lot of Algol code before. But the text was about 99.7% accurate. There were very, very, very few typos on a 30-odd, 40-odd-year-old TypeScript. Yeah, it's just incredible. And neural networks again. All of those organizations, and an awful lot of others, have told the world that they're using neural networks. These guys haven't been quite so forthcoming. Anyone know what that building is? GCHQ, our equivalent of the NSA. So they don't talk that much, but I think you can find them on Twitter these days. However, their tweets are usually fairly cryptic. What's really surprising is that many of those companies have actually open sourced the software which they use for building neural networks. And at first sight, that seems kind of crazy, because they're giving you a chance to take the crown jewels. But of course, the one problem with neural networks is that they tend to need an awful lot of data and an awful lot of computing power to learn to do something really useful. Once they've learnt it, then you can run the resulting neural network on a very, very much less powerful device. Quite often, for instance, you'll be running neural network software on your mobile phone if you use any kind of speech recognition capability. But the weights from those networks will have been trained using probably hundreds of millions of items of data over many, many, many CPU hours. So I too got back to neural networks, converted my Dyalog16 code originally to Python and then more recently to APL. I've been blogging a bit about it, busily stealing code fragments from assorted friends in the community. And I thought I would show some slightly more attractive code than the stuff we looked at yesterday. That's really the core of the very limited implementation that I did back in 1974. It has quite a small group of neurons, as you can see, because none of the numbers in the array shaping are that big. But essentially, that's the code that tells you the way that the cerebellar cortex works. It's kind of compact. If you take a look at what other people are using, almost all of the current tools have at least their front end implemented in Python. One or two exceptions for that. And that's a little sad, because if you take a look at the Python implementation for a single neuron, there's quite a lot of code, and that's a bit better. Okay, I'm nicely under. I'm pretty much done. Oh, I have an update to this, actually. The raw APL is indeed about 100 times faster than Python. And, hey, I can run that neural network, which used to burn up significant amounts of university computing power, on a $5 Raspberry Pi, and get acceptably fast results. With about 50,000 times more neurons as well, which is quite a plus. Most of the code which runs on Python, as opposed to generating stuff that runs on GPUs, uses a library called NumPy, which is a Python wrapper for some reasonably optimized C code, which has been influenced, though not enough, by APL. Basically, NumPy's APL's done wrong. And we did a couple of quick timing tests. I think it was 5 times faster. APL was 5 times faster in one case, and certainly at least twice as fast in another. So actually there's quite an advantage in that space. But that's going to get much better if you've got more than one core available, because generally speaking, all of the operations that one's doing with the real neural network involve arrays that are big enough that the APL interpreter will smartly say, I'm going to chop that up for you, and then stitch the bits back, and you'll never even notice what I've done, except it's going to be faster. And for some of the stuff I'm doing, I got something like a 3 times speed up on a 4-core machine for free. Not on everything, but on some quite important operations. Of course, it's much slower than you might get on a fairly powerful array of GPUs, but by the sound of things, I may be able to take advantage of that speed pretty painlessly from APL within a reasonable period of time. So, for me, I wonder whether this isn't potentially a tipping point for APL. There's an awful lot of work being done in neural networks. And one of the interesting things is that the language they've used used to be MATLAB. Almost everything that was done was published in MATLAB. And now, almost everything they've done is front-ended in Python. And so they're willing to change. And my hope is that we can encourage some of them to at least do some of the exploratory stuff in APL. Because great though the tools are that Google and the others have open sourced, they're great so long as they've already thought of what you want to do. And as it happens, it's almost impossible for me to use them for the particular sort of networks that I'm playing with. It's a lot of work. It's at least as much work as it would be to code it in hand code in Python, and a lot more work than it is coding it in APL. So I'm going to be trying over the next year or so to get out and talk about this when I get opportunities to the non-APL community, and just see if I can get some more people experimenting. I guess that's it in terms of time. Open for questions.
Oh, thank you for the talk. Very intriguing stuff. And did I understand correctly that your background is partly in neurology, or totally, or?
No. That was the background of David Marr, my supervisor, but he actually started off as a math major. My interest in neuroanatomy goes back to then, but I'm strictly an amateur. I've spent all my working life as a developer or a trainer or coach in IT.
In?
Information technology.
In IT, I see. Okay, the reason I prefaced that, what's on my mind is, from the beginning of your talk, and there were a few points later, especially when you mentioned Golgi cells, that reminded me of a book that impressed me very much when I read it 30 or so years ago. And I wonder if you're familiar with a book by Pentti Kanerva called Sparse Distributed Memory.
I think I read it about 20 years ago.
Yeah, okay.
And it's actually on my list of classics to repurchase. But thank you for reminding me of that. There was quite a lot of work done back at that stage that I think is still very relevant and has, in some cases, been underexplored.
Yeah, it's just to clarify, it's similar, it's at least related in the sense that that book deals with an explicit mathematical model of memory, and late in the book he shows this rather striking fact that that the structure of parts of the brain, which I gather from your talk is the cerebellum, is very suggestive of what you do to implement his model.
Yeah. Thank you. Yes, I'll certainly push that up the list.
I'm always interested in real-life applications, and you've already shown us some of the areas where neural networks have been applied, such as Google. You also showed a very intriguing picture from GCHQ. These days, one of the new expressions that I come across quite a lot is deep learning, which to me is sort of an extension of what you've just talked about, where people basically start with what they call an empty brain, and the brain then learns quite a lot of stuff. And it is particularly in use in the biometric area, for example, for facial recognition. So do you see that the kind of work that you do in terms of robotics and informatics is at some point going to correlate into the biometrics area?
It's already being used for that kind of thing. And it's worthwhile saying what I understand by deep learning, which is simply learning using neural networks which have many layers, and usually learning what's important as well as being told what the output should be. So effectively, deep learning networks are just neural networks with a lot of layers. And they're all, as you say, they're already being used for all kinds of stuff. One application which I find absolutely fascinating because it hints at some extraordinary potential. One group has, it's actually a group of people around Hinton in Toronto, whom we talked about yesterday, have done work on a pair of neural networks which are each capable of being driven either way round. Okay, so the neural network can either receive inputs and attempts to classify them and produce an output, or you can provide it with the output and expect to see something recognizable at the input side. And people have done that with images. That's kind of cool. You end up with a recreation of the image which looks a bit as if you've been taking substances that you probably shouldn't. But they've also applied this to neural networks which have internal feedback, recurrent neural networks, which are quite good at processing language. And in the forward direction, one of these networks will take typed text and turn it into a vector which represents the meaning of that text. And if you run them backwards, they'll take a vector which represents the meaning of that text and create a string of characters which utters it, in effect. And so you put them back to back and you've got machine translation. And it's about as good as the best state-of-the-art translators are, which is pretty poor, by the way, but it's still impressive. Okay.
Okay, so we need to be looking at tiled matrix multiplications running on the GPU first.
Well, that would make me very happy.
Great, thank you very much. That's
okay.
fascinating.